Welcome back to the deep dive.
Great to be here.
So today, we're talking to anyone who's ever run a high-volume manufacturing floor. You know, the kind of place where every single millisecond is money.
And every broken tool is just a complete catastrophe.
It is. It really is. We're diving into a decision that honestly defines a machine's efficiency, the feed system for your CNC drill.
And that's really where we need to start, because I think the common mistake is just to look at the initial price tag.
The capital expense, right?
Exactly.
Yep.
You compare a big hydraulic system to an advanced servo drive, and you just stop there. Our mission today is to get way past the sticker price. We need to focus on the mechanics.
Power and speed.
Power and speed. It's a real philosophical split. Are you optimizing for raw, unyielding muscle? Or are you going for, electric millisecond by millisecond precision?
We're pitting the heavyweight hydraulic, the muscle, against the agile digital brain of the servo.
And the stakes are huge. I mean, we're talking about cycle time reductions that can be anywhere from 30 to, in some cases, 70%.
Just from this one choice.
Just from this choice. A hydraulic system gives you that stable high thrust you need for deep holes. The servo, though, it's a sprinter. It's about blistering acceleration and exact positioning. Perfect for high volume, for complex tapping.
Okay, let's unpack that. From the machine floor up, the difference is obvious. You see hoses and pumps versus wires and motors.
Yep.
But I want that inside view. The stuff that really determines performance and, maybe more importantly, prevents all that downtime. What's the core logic here?
Well, it all comes down to energy conversion and the control philosophy. Let's start with the hydraulic system. Its philosophy is purely, let's call it force-oriented.
Force-oriented.
It generates linear force by pumping oil into a sealed cylinder which pushes a piston. Simple, powerful, and it has a very high power density.
So you're literally just squeezing a massive constant load right onto the drill bit. It sounds incredibly robust.
Oh, it is. It's very robust. But here's the trade-off. To maintain that pressure, the pump station often has to run constantly.
All the time.
All the time. Just to keep the fluid primed and ready. So that translates into high energy consumption, even when the drill is just sitting idle.
And the maintenance.
The maintenance is inherently messy. Let's be honest, you're dealing with pressurized fluid. That means oil leaks, filter changes, replacing seals. It's a constant battle.
I've seen a ruptured hydraulic line before. It's not pretty. That kind of hassle has a real impact on labor costs, on cleanliness.
It absolutely does.
Okay, so now shift us over to the digital side, the servo feed.
The servo system operates under a completely different idea. We call its philosophy position-oriented.
Okay.
So it replaces that whole messy cylinder with a high-precision electric motor that drives a ball screw and nut assembly.
So instead of a brute force piston, it's more like a finely tuned robotic arm.
That's a perfect analogy.
Okay.
And the genius is all in the control logic. It is fully closed-loop control.
We hear closed loop thrown around a lot. What does that actually mean for the operator on the floor?
It means the computer is constantly, and I mean constantly, self-correcting. The hydraulic system just applies force based on how much a valve is open.
Right.
A servo, on the other hand, uses these high-resolution encoders. We're talking about thousands of position checks every single second, and it combines that with complex PID algorithms.
Okay, for those of us who might have skipped robotics class, what's the PID algorithm doing here?
Its job is instantaneous regulation. So PID stands for proportional integral derivative.
Right.
But think of it like the brain that is constantly tweaking the power to the motor. If the drill hits a slightly harder spot in the metal, the encoder signals a tiny lag.
And the PID algorithm just instantly corrects for it.
Instantly. It adjusts the voltage to maintain that target feed rate, that target position, down to the micron. No hunting, no drifting. And the system is cleaner, it's a simple lubrication, and critically, it only uses power on demand.
Only when it's moving.
Only when the motor is actively moving the tool.
Wow. Okay, so that distinction, force-oriented reliability versus position-oriented precision, that's the foundation.
That's everything.
Let's move to the metric that every production manager lives and dies by, cycle time. You said fast retraction is a game changer. How do these mechanics translate into actual speed?
This is where the servo just is. It just leaves hydraulics in the dust. We're talking about dynamic response in milliseconds.
Not tenths of a second, milliseconds.
Milliseconds. I mean, you can't overstate that difference in a high-volume shop.
Yeah.
A servo system can achieve a dynamic response over 100 hertz. It can go from its slow-cutting feed to rapid retract in less than 20 milliseconds.
Wow.
There's no fluid inertia, no valve delay, nothing to overcome. And this allows for just stunningly high acceleration. sometimes between 10 and 50 meters per second squared.
10 to 50 m squared. That sounds less like a drill and more like a rocket launch.
Yeah.
How do you get that kind of acceleration without just snapping the tool?
That is the secret of the S-curve acceleration profile. It's like a digital shock absorber. So instead of just slamming the motor to max power, which would be a harsh square wave acceleration, the S-curve ramps the acceleration up and then ramps it down smoothly. It's incredibly fast, but it's controlled. No shock to the tool or the machine.
And that speed is what delivers those huge cycle time savings.
It is. The retraction speeds can exceed 30 meters per minute. And if you have a job with hundreds of holes, the time saved just on that rapid movement, it really can slash your total cycle time by 30, maybe even 70%.
So if the servo reacts in under 20 milliseconds, what's the delay on the hydraulic side for a reversal?
The hydraulic system is just inherently sluggish. Its response is typically under 10 hertz.
Okay.
So when the controller says reverse, the valve has to physically shift, the fluid has to compress, the flow has to reverse direction.
It's a physical process. You can't avoid that delay.
You can't. And that delay can be anywhere from 50 milliseconds up to 300 milliseconds.
Correct.
That pause, which is, 3 to 15 times slower than a servo, adds up to hours of lost production every single week. Hours. And its acceleration is much slower, too, maybe 1 to 5 meters per second squared. If speed is your main goal, hydraulics will always be the bottleneck.
Okay, so the digital brain is the clear winner for speed. No question. But let's challenge that. Faster isn't always better.
Right.
Sometimes you need that raw, unyielding push. Where does the brute force of the hydraulic system become not just useful, but absolutely essential?
This is the hydraulic stronghold, no doubt about it. When you're fighting intense, continuous friction, and you need absolute stability under maximum load, you have to go hydraulic.
So what's the benchmark? When does the load become just too much for a servo system to handle efficiently?
We're talking about deep hole drilling. The rule of thumb is an LD ratio that's length to diameter of more than 10 to 1, sometimes up to 100 to 1 in gun drilling.
100 to 1?
Yeah. You need that continuous, relentless push that hydraulics offer to fight the friction over that huge distance. They can give you 20 to 50 kilonewtons of constant thrust without ever overheating.
And what about just huge diameters if I'm trying to drill a really massive hole?
Any hole that's, say, 30 millimeters or larger, that usually tips the scale to hydraulics. To get the force you need to drive a 50-millimeter drill into high-tensile steel, you need a servo motor that is just enormous.
And prohibitively expensive.
And probably water-cooled. It just becomes impractical. Hydraulics handle that raw load naturally.
I also read that there's a hidden advantage with hydraulics in terms of heat.
Yes, absolutely. The oil in a hydraulic system isn't just transmitting force, it's constantly circulating.
Right. Back to the reservoir.
Back to the reservoir through the filters, and that circulation is constantly pulling heat away from the cylinder, away from the point of highest stress. A servo motor, under that same continuous max load, will just build up heat in the windings, and that limits its duty cycle.
That's a huge point. Now, what about shock absorption? You're drilling into rough castings, you hit a hard spot, a weld. That's when tools snap.
And this might be the biggest safety factor for hydraulics. When that drill hits an internal void or a hard spot, the oil in the cylinder acts like a soft, liquid spring.
It has some give.
It has some give. It absorbs that shock. A really stiff, digitally locked servo is always fighting to maintain its exact position. So it might just try to force the tool straight through that hard spot.
And snap.
And snap. So that lack of stiffness in the fluid is actually a feature, not a bug, in those rough environments. Plus, you can easily add pressure sensors to the hydraulic lines. This system can literally feel a spike in force from a dull tool and retract before it breaks.
Okay, let's shift back to finesse. If you're making high-value parts, threads where integrity is everything, why is tapping the job for a servo?
We're back to that position-oriented philosophy. For an operation like rigid tapping, your feed rate has to perfectly match the thread pitch.
Perfectly.
Perfectly. If you're cutting a 1 millimeter pitch thread, then for every single 360-degree rotation of the spindle, the feed axis has to advance exactly 1 millimeter. Not 1.005, not 0.995, exactly 1.
And if you're off by even a tiny amount, you're either stripping the threads or breaking the tap.
You got it. Servo drives electronically lock the spindle's encoder to the feed motor's encoder. They move in perfect digital sync. You get pitch accuracy within plus or minus 5 microns.
So you don't even need those expensive floating tap holders.
Often, you don't. You're relying on pure digital precision.
And that speed advantage we talked about before must be critical in blind holes.
Oh, it's the difference between success and total failure. In a blind hole, you have to stop and reverse the tap instantly before it bottoms out.
Instantly.
That hydraulic lag of 50 to 300 milliseconds is a disaster waiting to happen. The tap just keeps moving forward after the reverse command is given, and snap. The servo reverses in milliseconds. The risk is minimized.
And how does that micron-level positioning help with something like peck drilling?
Peck drilling is all about clearing chips. You drill a bit, retract, then wrap it back down to the exact spot you left off.
Exact is the key word there.
It is. A hydraulic system can struggle with that. It can drift because of fluid temperature changes. And if your position drifts even a little bit, the tool smashes into the bottom of the hole when it rapids back down.
Another broken tool.
Another broken tool, another scrapped part. The servo, with its closed-loop encoding, knows its absolute position down to the micron. It pecks, retracts, and rapids back to the last cutting depth perfectly every single time. No collisions.
So, if we pull this all together, we're really comparing a system based on constant calculation. The servo's control is predictive
It's all algorithms and position data.
versus a system based on simple force output. The hydraulics control is reactionary.
It's just reacting to pressure. That's the central takeaway right there.
Fantastic. Okay, so for the person listening, making this critical decision for their shop, let's just run through the final synthesis. What's the ultimate decision matrix?
The choice is really defined by the application's #1 priority. If you need continuous, immense, stable thrust for really big or really deep holes,
And you need that shock absorption.
and you need that shock absorption, you choose hydraulic.
Yeah.
But if your main goal is maximizing speed, saving energy, cutting down cycle time, and doing high-precision work like tapping, then the servo is the clear winner.
So it really comes down to force-oriented reliability, that hydraulic brute strength, or position-oriented speed and precision, the servo's digital brain.
That's the choice.
Mm.
And, to leave you with a final thought to mull over, we've established that the hydraulic system is messy. It's constantly running. It needs this steady, expensive diet of maintenance leaks, seals, filters.
Right.
So I'd ask you to consider the total long-term impact on your business, not just the cycle time, not just the upfront price,
Yeah.
but the hidden cost of downtime. Which system truly aligns with your maintenance team, your capabilities, and your long-term budget? Because at the end of the day, reliability and uptime, that's where the real profit is made.